Let's go on with our teaching by analogy. We found in the third part of this class that there was this principle that was the basis of all rocket science. And that was that if we could isolate a system so that there were no external forces on that system, or that the net force was zero, then we had this quantity that we called linear momentum that was conserved. No matter how messy the collision or what was going on, it was conserved. And that linear momentum we found was the mass times the linear velocity. And it was a vector quantity. It was in the direction of that velocity vector. Now what that means is if you get out of your space station and you just kick off the side, well, that momentum that you've got is just going to keep on keeping on. And you're just going to keep on going with that same velocity forever. Okay? Now, by way of analogy, if we can isolate a system so that there are no external torques, or that all of the external torques balance so that the net torque is zero, then there's going to be a quantity that's conserved or stays the same that we call angular momentum. Now think for a moment. If linear momentum is mass times linear velocity, what's this angular momentum going to be? What should we have instead of linear velocity? Well, it makes sense to me that it should be the angular velocity. Okay? And instead of the mass, we found that when we are rotating, it's not the mass that matters, but the moment of inertia. And so the formula for angular momentum is the moment of inertia times omega, the angular velocity. Now remember, these are vectors. Omega is a vector. And you remember the direction of that omega was given by right-hand rule. If I rotate my fingers of my right hand in the direction of the rotation, my thumb points along the axis in the direction of the omega. So right now, this wheel has an angular momentum. Well, linear momentum is how hard it is to stop something from moving down the road. Angular momentum is how hard it is to stop something from rotating round and round. Okay? And in both cases, they have direction. Now, let me see if I can illustrate this. I have here a disc on a little axis, and this axis has been balanced with these masses here so that the net torque on the system is zero. I'm going to use this string to spin this up. Oh, and the string broke. Okay. Well, let's just... we'll try that again. We need a better string. Okay. So... And it broke again. Oh well, such is life. Now, I got that disc spinning in such a direction that its omega vector was out this pole here. And that means its angular momentum is also that direction. Now what you see is that if I pick that up and move it, the disc always keeps spinning with the same rotational speed, but also the same direction. And I can do a little dance, make a little dance. Anyway, we call that a gyroscope. And that has important applications that you've taken advantage perhaps on Segway. It has military applications. If you've got a gyroscope that's always pointing in the same direction, you can have a smart missile. if you put 3 gyroscopes in the cone of a smart missile, one that's pointing north and one that's pointing east and one that's pointing up, then no matter where that missile goes, it will always know what direction is north and what direction is east and what direction is up. And that means it can follow a digital map and find its target. Now, here's another illustration of that principle. If I spin this wheel that has been, it's got a lead layer around it to give it a very large moment of inertia. If we were a rich school, we'd have a machine to do this. We're a poor school. Now, right now, it has a moment of inertia that is in the same direction as the angular velocity, meaning towards the ceiling. Now I've isolated myself by putting myself on this stool that is free to rotate. Now if I force this wheel to go upside down, I suddenly change its angular momentum from up to down. Well, the angular momentum of the system has to remain up. And so I have to start spinning in the original direction of the wheel. Now, you can see what you could do with that. If you're in some sort of satellite in outer space and you want to go the other way, you could just turn a spinning wheel and change your direction. Now, that'd be more profound if it were going faster. But that's as fast as I was able to get it. Now, one last thing that I'd like to point out, and that is the only way you can change the mass of an object is by cutting part of it off or gluing something on, or if it's a human, diet or exercise. And I tell you, that's not working during this lockdown. Okay, so once you've got a certain velocity, linear velocity, because momentum is conserved and your mass is not changing, that linear velocity stays the same. That's what I was talking about when you leave the space ship and get pushed away. But we found that we could change the moment of inertia by putting the mass closer to the axis of rotation. And so when I say that angular momentum is conserved, that doesn't mean that angular velocity is conserved. And you've all seen this during the Olympics, the Winter Olympics. When an ice skater goes into a spin, he or she goes in like this, with their arms fully extended, trying to make as big a moment of inertia as possible. And then as soon as they've established their angular momentum, as soon as they get spinning, they pull in their arms, and that causes their moment of inertia to get smaller because the angular momentum has to stay the same. The omega has to compensate by getting bigger. Now I can show this in a way that's less humiliating by sitting on this stool, again, that's free to rotate, so that I get rid of any external torques. And I'm going to get myself spinning with the mass out here. And then I'm going to pull that mass in. Whoa! Whoa! Okay. Okay. That's the end of the lecture, folks. Thanks for tuning in. We'll see you for the review for the final in just a little bit.